All right, how we doing, everyone? Doing pretty good? Everyone's feeling alive? All right, so for those who stuck around and, yeah, let's look at the chat. Where is my chat? Oh, there it is. There's my mouse. Yes, sir. Easy. Perfect. So, if you've made it this far and stuck around this long, I guess, hooray. Because now we are going to be leaving the time domain. And today's lecture, we're going to go over a new happy domain that you probably maybe are or aren't familiar with. And that is the Laplace Transform. So remember, okay, so I've probably given you guys, let me show you. There we go. So if you were in class and I gave out the assignments, and by the way, let's look at how I got this assignment. Oh, if I press this back button, oh, look at that. And oh, what's that? Oh, Saturday, November 15th. Did I change the date right?
That's not a Saturday.
No, that's not a Saturday.
That's literally our Monday of our test.
I'll think about it.
You can just change it
I can
to Monday.
I can change it.
Mondays.
Yeah, it shouldn't be that bad, which can be found right here. And then you can see November 5th, lecture 12. Oh, click that. Oh, what's that? It's not on the server because we're recording it right now. And then lecture should begin. And don't worry, I'll go over a little quizzy that we have today, but I will talk about the Laplace transforms and how do we practically use them and how do we implement them. So if you remembered from class, well, I'll just go over the surprise right now, is that, well, let me see. Let me go over some things. Oh, okay. So all systems that we've looked at, so if we had some like signals x of t, right? We can represent any signal as like, oh, it just does whatever it wants, right? So we have these nice little signals, right, that just go around on time, but actually all signals have the definition. Remember that one exam everyone kind of did or did not do well on, where any signal can be described by some amplitude. We'll call it A, which is an amplitude, times e to the, I guess, alpha t, right? So all signals have an amplitude. And then all of them have, well, some like decay or something like that. Okay, remember that? So, and then actually, I can replace it where alpha can equal real plus some j imaginary. And why did I put imaginary? Well, because if you do e to the j omega, right? What does that correlate to? Actually, if I put a t right there, what does that correlate to? It's a sinusoid. And that means it basically just spins around like this, you know, periodically. Right? So all signals from chapter 1 can be composed of, well, real components, imaginary components, some input. And, well, this is just some generic whatever we have. So now, you remember all those systems we were trying to build? Okay, we have, convolution, we have these difference equations, and our total responses, ZIRs, ZSRs, we're all masters of that right now, right? Because we're going to be doing a lot of it after this point. So there's a domain, there's a beautiful domain that we can call, and that is the Laplace transform, where the Laplace, I'm going to just call it the Laplace of some signal x of t can be defined as, all right, we're going to translate this. So here's our signal, right? Here's the signal t, right? What we're going to do is, I'll just try to visually show it to you. Here's x of t, right? And some signal, right? Or just some random signal, right? Here's t, right? What we're going to do to this signal is we're going to look at every point of the signal. So from t is equal to minus infinity, right? The end of time, to the beginning of time. Okay? So we're going to go from minus infinity to t is equal to positive infinity, we're going to look at the entire signal x of t, right? And then there's a weight we can multiply that by, e to the minus st dt. So if you memorize this, that's all you need. You can pass this class with an A. Hallelujah, right? So that's literally the definition, well, like the raw definition of the Laplace transform. Okay, and then another notation I gotta show everyone, just in case there's a billion representations, but the way I'm gonna try and show everyone is this can also be represented as, let me grab another marker, not that marker, let's try the green one, is they would, Dr. Stubert or I would like to write it as x as a parameter of s. So this would be like a capital letter. Capital letter x. So what this basically means is we have some function, well, capital X, which is a function of s, right? And here's our t, right? And then we're just sweeping all this, we're just adding, and then, oh, there's our play variable. And then whatever we do with this, all the t's are going to be gone, they're going to be evaluated, and the only thing that'll be left over is s, which we can play with in the Laplace domain. So with that, I will show you one method I'll tell you right now. There's an important property I gotta tell you, and I'll show you on the next page. All right, so if you're gonna memorize one property, this is it. How to pass this exam. So there's a property of, all right, so let's talk about linearity. Where, how do you tell if something is linear? It's gotta be, what do you call it? It's got to pass the scaling property. Scaling property and additivity. Okay, right? So what I'm going to try and tell you is, actually, do I want to do this? Actually, yeah, whatever. I was going to try and get to the point where, like, okay, you have some y of t, which is equal to some x of t convolved with h of t. This is the raw definition of convolution, right? And if you were to, let's say, let's multiply this by some, I don't know, constant c1, right? That means whatever we do here, we're just going to get a c1 there. It's linear. It's scaling, right? We can pass that, right?
Yes.
And then the other thing is, what if we wanted to do plus x2 of t convolved with h of t c2 or something like that, right? Which can also, if I were to write it on the other side, plus c2 y2 of t, right? Right, you see that? This is just the basic definition of linearity, okay? So I'm doing this. This right here is equal to the summation of two convolutions with two different weight factors, right? So you see how linear this is? So there's one property I got to show you about the Laplace transform. And that's multiplication. So to just get it out of the way, if you ever see something like this, y of t is equal to x of t convolved with h of t, this is convolution. Okay, right? The rule is, if we were to go into the Laplacian domain of y of t, right? The rule that everyone's got to memorize is we're going to turn all the y's into its equivalent, well, into this. This is just, I'm just going to go over some practical stuff, right? But here's convolution, right? In the Laplacian domain, all convolution turns into multiplication. Okay? So, and then everything we've done from here, so if I were to rewrite this one more time, let me use the orange marker, okay? If I were to take this right here again, right, and rewrite it down here, okay, according to linearity, if I were to multiply y of s, right, which is multiplied by some gain, right, y1 of s, right, plus c2 of y2 of s, I'm just calling these random things, right, which is equal to, I'm going to look at this term, let me just do this. I'm trying to prove a little property right here. So this term right here, right, here's c1, right, x of s, h of s, right, that's the first term, and then the second term, just going to underline that, see that? x2 of s, h of s. And this is basically just says Laplace is also linear. Right? So what I'm trying to say is everything you've learned so far will still be used. So, oh, you see the scaling property, this additivity stuff, and then here's our multiplication property. Everything still works out the same. So if you add some Laplacian outputs, you can just add this too. You can have scaling and you can add them. It's all linear. Does that make sense, or am I going too fast, or am I going too slow? All right, so there's another thing I gotta show you. And maybe this will bring back 220 or 221 vibes. All right, hold up, there we go. So I just described, okay, we have y of s, right, which is equal to x of s, h of s, right? And then everyone's like saying, oh, remember how we had the y of t, right, is equal to x of t convolved with h of t, right? This is the impulse response, right? Right? Remember that? But in the Laplacian domain, I'm going to do this form. So I'm going to divide the input on both sides, and we're going to get the following. H of s is equal to y of s divided by x of s, which is, and this parameter, if you've remembered, is called a transfer function. All right? So what this basically means is, okay, we're just looking at the pure output divided by the input. The output divided by the input, and we're just looking at the transfer of the signal, the transfer of the power. So if I were to say this, like if this was V in, right, V in of S or something like that, and V out of S, right, whatever power we put in or out divided by in is how much our transfer function is. Does that make sense? Or I'm trying to get a little definition. This is what we call a transfer function. Does that make sense, or should I go over it again? Yeah, what's up? So right now we're just going to call it an output. It's just the output, the transfer function of the, well, not a transfer function, the Laplacian of the output divided by the Laplacian of the input. So right now I'm just going to treat these as just arbitrary variables for now, right now. But what I'm trying to say is if we had an input, right, and we have an output, right, the output divided by the input is a transfer function. Gives you this, h of s. Right? That makes sense? Like, well, you can do this in the Laplace domain. You can't do this in the time domain, because if you tried, you can't really do that, because this is basically some integral x tau h of t minus tau d tau, right? And you can't really divide h. You can't do it. Can't divide h. So we can't do anything here. We can't see the raw output divided by the raw input. We have to put it into this like transfer function. So this is one benefit that we get by moving into the Laplace domain. Does that make sense? Okay, so the next thing I gotta show everyone is, let me see, how do I explain this part? So everyone's saying, okay, what's this Laplace domain? So the Laplace domain is this nice special place. So if I were to draw L of S, so the Laplacian domain is going to deal with the S domain. So another name is S domain. S domain. Okay? Where we have a real axis and an imaginary axis. Okay? And all this is basically saying is, let me see how I want to put it. There's one definition I would really want to get to you. Should I just introduce it right now? Okay, I'm going to teach you practically. So remember all that region of convergence stuff? So one of the properties of the region of convergence is a property you got to know, and I'll write this in sentences. All poles must be on the left side of the imaginary axis. Plus, ROC is on the right side of rightmost pole. All right? So in other words, what I'm trying to say is if you have a pole right here and you have a pole right here, right? The region of convergence, we're going to look at the far right pole, whatever pole is on the right side the most. So this one's pole 1, P1 and P2. Which one's more towards the right? This right here. That means your region of convergence, ROC. All right? Does that make sense? All right, so another thing I'm going to have to introduce is, okay, how do I physically see what's going on with this Laplace transform? What does this mean? Can you like look at this and tell me what it means? No? Exactly. Don't worry, I'm here to help you. So if I were to show you the practical point of the Laplace transform, let me see if I have some notes on something crazy. Let me show you. So if I wanted to go from the Laplacian domain back into the time domain or some x of t, right? Actually, maybe I should call this L of t. What we're going to do is we're going to look at the entire domain, and the entire domain actually at a pole, I think, at this pole. Let me see what I do. ds. I integrate the entire ds. Let me just go over the raw definition. I think, let me show you your textbook. Let me see if I have that. You guys reading the textbook, by the way? Helpful? Confusing? Let me see. There it is. So one of the definitions I really want to hardball right now is this right here. First page, or actually page 3 of 321. So here's your little h of s. You see that right there? So what I'm trying to try and get to you is the output can be generated just by looking at these poles right here. So what I'm trying to say is, let me show you what I mean. We can technically add, so here's the S domain. Here's all this is S, right? We can go from minus infinity to positive infinity of h of s, and then I guess we can multiply this by e to the st ds, something like this. Just questioning. And actually there's like a 1 over 2 pi I, something like that. Don't worry about this. We're going to add every point in this Laplacian domain, but the thing that's going to stick out the most are these poles. These are like infinities. Okay, what happens when you do constant plus infinity? What's that equal to? Okay, so what I'm trying to say is, forget all these points. Like, okay, we're like this integral right here. This integral. Oh, someone's saying something in the chat. Let me see.
Oh, that's it. Okay.
Inf.
I didn't know
Oh.
if you had questions.
Okay. So this summation is saying, okay, we have to add all s points. But if we just add this plus an infinity, which is a pole, then we're going to get infinity. So what I'm trying to say is look at the poles. And we're going to show, I'm going to show you that on the next page. Page, okay, 3, page 4. Okay? So let's analyze this right now. So if I were to draw, let's use a black marker. Here, let's call this one 1, minus 1. And let's call this one minus 2, right? All right, what's the region of convergence? Look at the rightmost pole, right? Actually, oh, this is probably why you guys were asking. S domain, right? So what's the region of convergence? Okay? So now, if we were to go back into the time domain, right? All we're going to do is just we're going to look at all these poles. Because if we add all these points, the things that are going to stick out are these poles. And the thing I'm going to try and get to you is the general solution, y of t, is going to equal to h of s is equal to pole, or something like that, times, let me see, e to the st, so s pole. Okay? Does that make sense? So these are s. Okay, here's real of s, right? Here's imaginary of s, right? And this right here is an s is equal to minus 1, right? And this is s is equal to minus 2 right here, right? So what I'm going to try and show everyone is y of t general solution. Actually, no, this is general solution, where for this example, the general solution of this graph is basically whatever magnitude this is. I'm just gonna put a1. Actually, I'll talk about that too. Actually, h of s1 e to the s1, right? T, sorry, plus h of s2 e to the s2t. All right, and if I were to solve for this, you're gonna get h of s1 e to the I'm gonna call this one 1 and this one 2, right? This one here is, okay, plus h of s2 e to the minus 2t. And then this would have a unit step. You see that? You can read any of these diagrams now. Does that make sense? Are you seeing this now? So, okay, now someone's probably asking, what's this? All right, so we're adding infinities, right? Here's infinities, right? Infinity. Infinity 1 and infinity 2. Okay, so what happens when we add two infinities? You're gonna get some type of infinity, right? But what I'm trying to say is some infinities are bigger or smaller than other infinities. So there's a thing called a residue. Let me write this right here. Big infinity. So there's a thing called a residue. Where each of these infinities are gonna have some type of thing shining out of them. Like, oh, you're gonna see like these tents or like these big poles. Like some poles are bigger than others. So if I were to draw this on the side, so let me see if I were to look from one side right here. Let's tip this over. Here's the real axis, and this right here is the imaginary. Right? We're just looking at it, instead of looking at it like this, we're just turning it like this, right? What you're gonna see is, okay, I'm gonna give this okay, let's call this one 2 times infinity 1, right? Whatever the gain is, right? And then I'm gonna call this one 4 times infinity 2, right? So I'm just assigning this one a number of 2 and this one a 4, right? Gains. So if I were to see these tents, they're gonna look like this. So here's minus 2, here's minus 1, right? And here's 0, right? You're gonna see something like this. This pole is bigger, so that means you're gonna see something like this. and then maybe something like that, and then this one also is like this. It's like tiny, and then something like that. So you see this right here goes to infinity, but this infinity is bigger than this infinity. But either way, they just go to infinity. But which one's bigger? So this is gonna have some like residue. This right here. So it's gonna like have something shining from it. Okay, does that make sense? So what I'm trying to tell you is, if you're just looking for the residue, okay, let me rephrase this. So to look at a Laplacian domain, one of these types of figures, all you need is a residue 1, and a pole. See that? And then residue and pole. And that's it. You can do whatever you want. You can solve any of these problems. Is that clear? Is this making sense practically? Because the theory is like cool, but we're trying to get stuff done. And now someone's asking, okay, David, why does the pole have to be on the left side and not on the right side? And that's a great question. I will show you that right here. Okay. So if I were to draw another graph, and I'm going to draw a pole right here, right? -2, right? And what happens if I draw a pole right here at 2? All right, and then let's just say this one has a residue equal to 2, right? Residue is equal to 4, right? I'm going to assign these residue values, just some magnitudes, all right? So if I were to find, actually, let me do this. The output of this, right? It's going to equal, well, whatever this is, residue 1 e to the minus 2t, right? See that? Plus residue 2 e to the positive 2t. So now, take t to infinity. This one right here converges. This one blows up. You see that? That's the reason why if we were to do this region of convergence, you see this? Okay, actually, let me show you one more thing. See this imaginary axis? This is like our r is equal to 0, right? This is like the point, like, oh, we're between the left side and the right side. If the region of convergence does not include the imaginary axis, your system is unstable. I'll tell you that. If ROC does not include MS, system, is unstable. Make sense, right? All right, so another thing I'm going to try and do on this piece of paper is, okay, we have poles on this real axis, right? What happens if we have a pole like right here, right? We have a pole right there. See that? I'm going to call this one P, let's call it, I don't know, P plus, okay? And you'll see why I did that. So y of, let's call this one something P, is equal to whatever value that is. I'm just going to call it re1 or something like that. E to the, okay, so this is the imaginary axis, right? So e to the, okay, let me show you this. S is considered, has a real plus j imaginary, right? Since there's no real part, we just have an imaginary part, right? That means we have a j, let's call this omega, j omega, positive j omega, right? So you see this is a signal, right? Is this a real signal or an imaginary signal? Correct. But the more formal definition is this is a complex signal. So we can't see, huh? So you can see that we can't see this in real life. So the rule is all complex poles that are where the imaginary part there's a imaginary part, has some complement. Okay? So this pole cannot exist without its little negative brother. So there's always this side right here. So we have a positive plus, and I'll probably do this. And does that look similar to something we've seen in class? And if I were to do this, 2 divided by 2, right? I think that's it. Cosine of omega, or actually t, and you get a sinusoid. Are you seeing this now? All right, so I'm gonna try and get to this final point before we start doing some math problems. Oh, chat. Okay, what's going on? Thank you for telling me that. Wouldn't it be multiplied by 2?
I was thinking that too. I was like, why is it 2 at the bottom?
Oh, thank you. Thanks, Ray. All right, you guys got to keep me on check. I'm running on 32 hours of sleep.
Fight that cookie again.
All right, ready for my ASMR channel, everyone? Oh.
Crumbs all over the.
All right. Well, that was a really good cookie, though. Should I just have lunch right now? Welcome to my food channel. All right. They did not teach me this when I was an undergrad, and I really wish they taught me this when I was younger, because I did not know how to read a Laplacian. So, here's your Laplace domain, right? If I were to draw this pole right here, how do you describe this pole? Or here's P1, right? That means y p of 1 of t, the output, you're going to see some decaying signal. So if I were to draw this with some magnitude, you'll see it respond like this, like this. Or actually, not ringing. It's a real part. It's real. Okay. Sorry. You see this? So if I have a pole right here, right, this is going to equal some like e to the minus p1 of t, right? That's a decaying factor, right? When t is equal to 0, then this right here is 1, right? Does that make sense? Okay. Now if I were right here, let's use the black marker. If I were here, p2, right? That means y of p2 of t, right, is equal to e to the p2 of t, right? Right? You see that? Where this is going to look like, well, here's 1. You're going to see something like this. Okay? All right, now, here is the cool part. What happens if we have a pole right here? What does that look like? You're right. So if I were to call this one P3, right? E to the, well, and then let's say this one times some VDD, right? Does that make sense? Are you guys able to read these plots now? Okay, and then, okay, there's a thing called like zeros. Like, let's say you have like a 0, but ignore it for magnitude. Okay, but affects phase. Okay, so we're not looking at the zeros. Our main focus is these poles. These poles are what dictate any system you have. Okay, now I'm gonna get to a really interesting one. So what happens if I have a pole right here and right here? All right, I'm gonna call this one P plus and P minus, where the S right here, S of P plus minus is equal to, has a real component, right? Plus minus some J imaginary component, right? Or J omega, right? So what is this gonna look like in the time domain? Y of P plus minus T. So you know it's on the right, on the left side, right? When we have a pole on the left side, it's going to look like a decaying function, right? But when we have this sinusoid, right? When we have these sinusoids and if we have an imaginary part, we're going to have a periodic signal, right? So that means our outcome here is 1, right? You're going to see some signal that does, like, it's periodic and it just does this. That's what that basically means. And actually just decays down to, actually just goes down to 0. Does that make more sense, everyone? Can everyone start reading these in 370 when you guys take that next semester? No. So that's what I wanted to get to everyone now. Like, does everyone, like, because I was seeing everyone in class, like, looking at these plots and they're like, this is cool, but how do we, like, physically see it? Is everyone good? Chat, you guys good? Hope so. All right. So one thing I want to get to. Oh, yeah, someone did say something. Yeah. All right. One thing I'm going to get to, everyone, is let's go over this little quizzy thingy. So we're going to try and get some practical stuff done today. So given this little quiz that I've given you, everyone, is consider the following RC circuit. You guys missed that circuit? Is all these fights? So, describe the system with differential equations. Can everyone do that here? And then I even give you guys a little hint. That make sense? I gave you guys a little hint.
Oh, okay.
All right? So we're going to try and do this. I'll show you guys. Don't worry. And let's just do it for a general equation. Plus minus. Guys missed that? T, V out of T, right? All right, so what do we do?
Walk the circle.
Pick a direction. I'm going to call this IC for reasons. So plus minus, right? And then let's take off, KVL. So V in of T, I'm going to go up the stairs, and I'm going to go down the stairs, minus I of C of T, R, right? And then minus, this is V out of T, right? Does that make sense? Is everyone following this? Remember your 221? Is your education worth it? No. And then all we do is, you see this current right there? There's a rule for all these capacitors. IC is equal to C dV out T dt. Got it? And then all we got to do is replace it. So just replace that right here to get the following. V in of T minus RC dV out of T dt minus V out of T. And then we're going to solve for V out. We're going to keep V outs on one side and V ins on the other. So I'm going to skip maybe one little step. Actually, let me just do this. RC dV out of T dt plus V out of T is equal to V in of T. All right? Making sense? But we're going to put this in a form where I'm going to divide the entire thing by RC, where we get dV out T divided by dt plus 1 over RC V out is equal to 1 over RC V in of T. Does that make sense? Easy? 5 points on the exam. Done. This is where people get lost. Now you guys can do that. All right. So now the next thing I'm going to try and introduce to everyone to get us back into the signal domain is, see this is V in a T, right? What I found, I call this one X of T, right? And here's V out of T. Let's call that Y of T, right? Then we can replace it into something more friendly, dy of T dt plus 1 over RC v, y of t is equal to 1 over RC x of t. Does that make sense, everyone? So now we have it into something that we're already used to, signals domain. So now, remember from 221, everyone was doing all this Laplacian stuff? All right, there's another practical thing I'm going to teach. I'll try to go over that maybe in the next lecture. Actually, let me do this one thing. Let me lock this pin. Boom. Isn't that much better? There we go. So one property I'm going to tell you right now is the Laplacian differentiation. But not just any Laplacian differentiation. This is the unilateral Laplacian transform. So if I were to show you a table, let me see. Do I have my table here? Where's my table? Let me see. Where is it? Aha. Where's my table? Hold up. Give me a moment. There we go. Actually, I'll show you this. So the thing I'm going to try and show everyone practically is, let's see. Here's my thing. There you go. Is all these d to the nth power, right? All of these differentiation things, we're going to replace it with the following, and let's see if I can fit all this into a piece of paper. Should I? Okay, let's do it. S of n, right? So this is something you're going to memorize. I'm just going to show you guys, and then everyone's going to look at the actual theory behind this on Monday. S of n, let me see, capital Y of s, right? Minus S of n minus 1. Y of t is equal to 0. Remember that stuff? And then minus or plus minus, let's see this. S of n minus n, right? Times d of y of n minus 1 t dt, where this is t is equal to 0 minus. That right there. Is that making sense? A little bit? Okay. Memorize. Okay? So all these differentiation thingies, we're going to replace it with something like this. The reason why it's called unilateral is because we're looking at just from t is equal to 0 minus to infinity. We're just looking at a causal system. Okay? Is that making sense? We're looking just at purely what happens at time is equal to 0 into infinity. Okay? So if I were to go on the next page, let me show you this. What page is this? I feel like this page was 6. This is 7, I guess. There we go. And, hopefully I still have pieces of paper left. Yes, I do. There we go. So dy of t dt plus 1 over rc. Does anyone get bothered if I replace this with tau? Where tau is equal to rc, right? 1 over tau y of t is equal to 1 over tau x of t. Okay? So then if we were to do our Laplacian domain, so we're going to go into the Laplace domain of this, of the whole entire thing. Analyzing this part right here, using our little a little formula that we came up with, which you will, I think Dr. Stuber already mentioned this in class. Also, he'll mention it on Monday. Is we're going to place this first term with, since it's a first order circuit, s to the power of 1, y of s, right? Minus s to the 0, y of t is equal to 0 minus. Everyone's getting that? And then we're going to look at this one right here. Plus 1 over tau. S of, since this is a first order or a 0th order circuit, S0, right? Y to the S. And then there's nothing after that. It's just 0. We're done right there. Does that make sense? Equal to 1 over tau. And then just based on looking at this, y of t, x of t would consequently be x of s. Is everyone getting that? We're good? Okay. So now the one thing I'm going to try and show everyone is we're going to try and get it to the point where we get h. We're trying to find for h. So you see this y of s and this y of s? We're going to try and group these together in the following. Y of s, pulling these out, s plus 1 over, I'm going to write this, rc. See that? Is that giving you vibes? And then this term just stays right here. Y of t is equal to 0 minus. Right? Is equal to 1 over tau x of s. And now all we do, actually, I'm going to skip a step by moving this to the other side and then dividing the entire thing by y of s. Or not y of s. Divide the entire thing. Actually, no, let me show you this. Y of s is equal to, actually, let's divide the entire thing by s plus 1 over rc is equal to 1 over, is that how I want to do it? rc. I think I realized my mistake. I'll show you guys what I mean. 1 over tau. Yes. S plus 1 over rc plus and there we go. Does that make sense?
Are you missing the x of s?
Oh, x of s. Yes, you're right. Here he is. X of s. Make sense now? All right, so one thing I'm going to try and tell everyone and is you see this right here, right? We have y is equal to t is equal to 0 minus, right? What does this indicate to you? What does this mean for you practically? So remember our little thingy right here, right? Our little RC filter, right? Our RC circuit, right? There's a rule that we remember from circuit theory is this has memory. Right? It's got some voltage. It's got some water. An initial condition. So what happens if we have, let's say our initial condition is 0. We have 0 conditions. We have 0 memory. What does this mean about this first part? This right here, if we have no memory, that means we're looking at 0 memory, 0 state. So that means this is basically our ZSR. But I'm going to put a quote on S because in the Laplacian domain, there's no such thing as a Dirac delta. But we're looking at this. This right here is our transfer function. Well, if we wanted to do y of s divided by x. This right here is the response, the impulse response of our RC filter. Is that really cool? Okay, so what happens if I ground my input? Let's say this input right here, I just ground it for some reason. If I just do this, right? What happens to x of s? It goes away. What's the Laplacian of 0? 0. It doesn't exist. So if I cover this up right here, then this basically is the ZIR of your system. And then what happens when you add both of them? Well, if this is a t, and then t if you wanted to, like, go back into the time domain, well, total Does that make sense? So instead of solving this, like, okay, in Dr. Baker's class, you guys were like doing all these crazy stuff. There's a second way of doing it. If you just ground your input and you just analyze your states and just add the input with no memory plus your input with, or no. How do I say that? You add the response of your system to an input plus the response of your system with some memory to get the total response. Is that really cool? And then if I were to write this on another page, let's do this. And if you were to write this on your exam, okay. Y of s, actually let me write this right here. 1 over tau, x of s, s plus 1 over tau, right? Plus y of t is equal to 0 minus s plus 1 over tau, right? See that? So, okay. Draw me the poles of the system. Where's our pole? So how do we get this to go to infinity? What? So, okay, here's s, right? Yep. So, not 1 over, okay. What value of s is going to make this go to infinity? So that means s pole is going to be located at 1 minus 1 over tau, which means if we were to draw our y of s, right? That means our pole is right here. And it converges. Does that make sense? So if I were to look at, well, actually, let's look at this term right here, right? Let's ignore that right here. So same thing with this one right here. It's going to have a pole right there, right? See that? Oh, there's someone in the chat. No one told me. Oh, thanks, Ray. Oh, okay. See this pole? Let's ignore this for now. See this value right here? What is this? This is just a constant. Okay? So that means just ignore that. If we have a pole right there, what does this tell you about y of t, right? If we were just looking at this. So if this is a constant, we're just going to look at whatever y of t is equal to 0, the initial condition, times e to the minus t, right? Over tau. Cool, right? And then I'm going to show you what this right here is, right? So this is a Laplacian divided by another Laplace function. So one thing I'm going to try and show everyone is, let me just rewrite this over here. Multiplied by 1. Actually, let's look at this. Okay. So if we were to look at this, y of s is equal to 1 over tau x of s, right? Right? That means h of s, right, is equal to y of s divided by x of s, right? Which is equal to 1 over t. I feel like I'm doing something wrong. Yeah, it's okay. 1 divided by s. Right? That makes sense? I feel like I'm missing a tau somewhere. Let me see. Okay. T. Okay, here's this. That's that. I feel like I'm missing. I feel like this one's ticking me off. Yeah, whatever. Point is, okay, see that right here? We found our h, right? That's our impulse response, right? Just I'm mimicking it, okay? So what I'm trying to say is if we were to rewrite this again, y of s is equal to x of s times h of s, right? And if we were to turn this back into y of t, right? Convolution. Okay, so that means this right here is, let me do this, 1 over t tau x of t convolved with h of t. And this right here is your total. response. Is everyone gonna get 100 on that problem? Good. Because then after this, once you find all your poles, you see how the circuit we took this circuit, we found the Laplacian, and we immediately got the impulse response. Remember all that, like kicking the boxes and like drawing block diagrams and everything? We didn't draw a block diagram. We didn't do initial condition. We didn't kick boxes. We just went into the Laplace domain and we got that. Cool, right? Less work. We didn't even think about that. So this is an easier way of doing it. And then look at this. Here's your initial condition, right? And then look, that's convolution, right? So that means all you got to do is, if he gives you a step response, for example, Vn of t is equal to 1 volt of u of t, right? Just a DC voltage, right? Can you solve for the total response? All right, let me show you one thing. Okay, and if no one's paying attention to this, it's gonna bite you in the butt. Let's stop being signals and systems people and let's be engineers. At TD is equal to 0, right? RC. And let's just say V out at t is equal to 0 is equal to 1 volt, right? What's this going to look like in the time domain? V out of t. So initially our V out is at 1, right? And what happens when we flick our circuit at time is equal to 1? We're going to have 1 volt here. We have a full bucket of water right there, right? We just have 0 right here, but we just flicked it at 1, right? So what is our output? Trick question, right? We have a full bucket of water. We switched that 1. 1, 1. What's our current? 0, right? So that means this bucket's always full. If he does this to you on the exam, this is really trivial. Does that make sense? All right, so what happens if I were to do the same problem, but instead of it being at 0, let's say it's at 10 milli, right? Or 10 milliseconds, right? So what are you going to initially see? So let's just draw it again. So our bucket's full right here, right? And this is V out of t, right? With TD is equal to 10 milliseconds, right? Actually, what's our tau time constant? If I were to do 1K and 1 micro. 1 milli, right? So that means it takes 5 time constants. So if we were to do 5 right here, 5 milli, right? If we just have, if our switch doesn't turn on, like, oh, see, it only turns out at 10, right? So that means after 5 time constants, if we have a 1 right here, 1 volt, right? What you're going to see is this, right? The bucket just empties. And then what happens at 10 milli, right? We flick the switch. What happens? Remember the charging equations? Does that make sense? There you go. And then right here is like 15 milliseconds. Cool? And you see how these shapes are like, this one's an exponential that's decaying and this one's a charging. If you move this delay right on top of this, you get that DC. Cool, right? So what I'm telling you is if he tricks you with putting a delay here, you see that right there? You can just shift these signals. But if he does this, he's really, really trying to get you to be trivial. And you get this DC signal. And if I were to show you your quizzy thing, convert the differential equation into the Laplace transform. Everyone can do that. And then identify the 0 input, 0 state responses, right? Sketch the region convergence. Everyone can do that now, right? And then solve for the total response. And then you can verify an LT spice. Okay, because someone's probably barking at me. Am I tricking you? Okay. Someone's probably not believing me. David, are you sure if we put 0 delay, right? Let's run that. Are you getting your money's worth? All right, so if I wanted to do, I really wish I can do this. Let me pull this out. So if we were to look at your assignment, and everyone can start this right now. Actually, let me just go over some stuff I'm going to show you, just for everyone to get started on this assignment. So I'm going to give everyone this nice little code right here. Actually, I'm going to show you the plot. Let me just draw this. That might be weird. Okay. So I'm going to give everyone this code to play with. No more coding. Okay? Lecture 12 or something like that. Okay? So what I did right here is I'm going to prepare the Laplace domain. So I have the real axis, right? And then I have the imaginary axis, right? I just prepared like, oh, this and this. So remember how I was showing you guys in the notes, right? That our pole is located at, let me see. Our pole right here is located at 1 over r, right? T, right? Tau, right? But our RC is 1 milli, right? Where is it? 1 milli, right? What's 1 over 1 milli? 1K. So that means that's the reason why I bounded my thingy. Let me show you. From 2K, minus 2K to 2K. So we're going to get a square. So we're looking at 2K from minus 2K to 2K, and we have a square right there, right? The real axis, the imaginary axis. So there's a function called mesh grid that just, okay, you have a line like this, right? And you have a line like this, right? So mesh grid just makes like this mesh that like does something like this where it creates a square based on a vertical and a horizontal line. So it just does this, and then it does this, and creates a big square with all those values in there. So that's what this function does. It creates a map. And then here's your S domain, which you can mess with. Okay, and then right here is our R and our C. And then let me show you one thing, because right now it's bothering me. Okay, so remember our H right here, right? Oh, let me see if I can do this. Oh, where's my mouse? There it is. Okay. See this right here, right? Our H, right? And if we want to plot purely the S's, right? We have a 1 over this tau times e to the 1 over tau, right? So what everyone's going to try and do is I'm going to do the following, and I think I see my mistake. H num, numerator, is equal to 1, right? We're looking at the numerator. The numerator, there's nothing. There's no poles. There's nothing. It's just a constant, right? Oh, there we go. H denominator, right, is equal to, let's call this one tau is equal to R times C, right? RC time constant, right? So tau dot times, just because I have OCPD, S, and then what did I do? Actually, no, not that. S plus 1 divided by tau, dot time, or dot divide. Okay? Has everyone seen that? And then because we're in the transfer function, all transfer functions are power. We have to convert it into power. So if I wanted, before I do that, H is equal to H num divided by, dot divide by H den, right? H power is equal to 20 dot times log of 10, because we're going to go into base 10, of absolute value of H. Does everyone understand that? The absolute value of H, so if we wanted to look into power, and then the log of it, and then times 20 to give us dB. Power. And now what I'm going to show you is the following. Figure 1. Okay? So, let me see. You see this h right here? And you see this denominator right here? And you see this s parameter right here. This right here is just like a blanket. It's just like a piece of blanket. And now we're just going to modify all this h depending, and we're going to sweep every value of s. And we're going to see the response. And let's see what that pops up. Oh, come on. Come on, MATLAB. There we go. Ah, yes, I got it finally, yes. You see that? So I'm gonna flip it like this. So, okay. So this right here is the real axis, right? This right here is the imaginary axis, right? If I were to look purely from a, oh, come on, MATLAB. Oh, this is a lot of power. Please don't crash. Oh, it's chugging. All right, I'm gonna have to redo that. Let me see. Here's my step. Oh, that's probably why. Let me make it 100. So I'm stepping from 2K to minus 2K to 2K in 10 interval steps. It's gonna be super precise, too much data. There we go, now we can see it better. Come on, MATLAB. Okay, now we're looking at like the plane like this. So you see that right there? That's our pole. And here's our real, here's our zero axis. Well, here's the real axis right here. Imaginary, we have zero imaginary components. There it is, and it's on the left side. And you see how it's going up like that? Pretty cool, right? And then, oh, so there's one thing. You've always wondered what a Bode plot does? So if I were to look at frequencies, right? Let me see. So let me show you what I'm going to do. So to look at a frequency response, right, or transfer function, right? Actually, I'm going to try and explain that right now, and I'll hopefully try to finish it really, really soon. Okay. Oh, 11. So there's one thing I got to show you guys. There's no time to explain this, but if you're in the Laplacian domain, there's a beautiful relationship with the Laplacian domain and its big brother, or its cooler brother, the Fourier transform, or the Fourier domain. And the Fourier domain exists right here. Okay, so if we just slice this and we look at r is equal to real is equal to 0, and we're just looking at the imaginary values, look at imaginary, right? Or sinusoids. Oh, yes? Which side would, since this is a right-sided function, it's on the right. Okay, so okay, here's my minus 1 over RC, right? See that? Oh, that means our region convergence is right here. Make sense? Yep, it's unilateral. It's a right-sided function. It only exists from 0 to positive time infinity, right? Okay, well, okay, sinusoids. Okay, we're looking at this domain, or periodic. Okay, so what happens if we just look at this? If we were to look at this, like, okay, here's a slice, right? And if I just flip it like this, you're gonna get the following. Which is equal to F2F, or frequency. So that means you're going to probably see something like this. See that? Where this right here is your 20 log of h of s. And then this right here is your pole. This is the Fourier domain from the Laplace. So what I'm going to show you right now, and let me see if I can do the next example. Should I just copy paste this? Yes, let's copy paste it. You guys like copy pasting? Yeah. You guys like that I do your assignment? getting my money's worth now. Let me show you. Okay. And no one should be complaining that I'm doing their assignments and not turning them in, right? All right, so our numerator is a 1, right? And the reason why I was doing this was I was doing something crazy. There we go. So there's a function called frex or frex, whatever you call it, right? So if you wanted to know what that was, basically frex is asking for just constants, coefficients. So if I were to do this, this one is basically asking for, let's look at the h num. You see this numerator right here? Just a 1, right? It's just 1, right? So that means we're just going to put a 1 right there, right? But this one's asking for 2 coefficients, where I'm going to show you this. Actually, let me show you this. Help frex. Let me show you that. If I were to show you this. There we go. So it's expecting. So you see this right there? So we have like s to the second power, s to the first power, s to the 0, etc. for the poles and the zeros, right? It's just expecting coefficients. So what I'm going to try and show you is, all right, here is our denominator, right? It's multiplied by tau dot times. We have an s right here, right? Power 1, right? So I'm just going to put a 1. That's the power, that's the coefficient that's in front of s, right? Then right here, or okay, let's see. I have a 1 dot divided by tau, right? Actually, I shouldn't be doing that. Let me do this. See that? Okay? And then I made a mistake here. Now I know why. Okay, so this is our numerator, right? And I'm doing a Fourier, so Fourier, right? Is that making sense? And then all I do is to get the total Fourier response, we got to take the numerator and the denominators and then sweep it by some W. What's my W? My frequencies are the negative frequencies, negative 2k, f is equal to 2k, and then the positive frequencies, right? Actually, if you wanted the frequency, you would have to do like this right here. Omega is equal to 2 dot times pi dot times f, where you can create your own thing, okay? So now, you know how to do that right there. That creates the actual Fourier response. Then you get the power, and then you get your angle, and then the reason why I did this right here is if you do angle, okay, let's see. You need to change h num. Oh, yeah, sorry, thank you. Let me just get to this one more, and then everyone should be set for the first half of the assignment. Fourier. I'm getting tired. There we go. There we go. You got that? See? And then, oh, I see. Okay, there you go. Don't worry, it's gonna bark at me, okay? So this is our power, right? There. Oh, oops. Don't worry, it's gonna bark at me. So to get the power, right, all we do is 20 log of this, absolute, right? To get the angle, you do this. However, this is gonna convert this to a radian by default. To convert it to degrees, you got, okay, this is radians, right? How do you cancel out radians? Divided by radians. But what do you replace it by? Degrees. So outputs degrees. What? Okay, now let's run it. Does that look like your Bodhi plot? Well, kind of, because I think what we gotta do is, let me show you this. No, I gotta show you this. This is really, really cool. Okay, there's a way to do something. Semi-log y. Let me do this. MATLAB. I need to show everyone this before we leave, because this is really, really like the pinnacle of this entire class. Semi-log of y. So, actually y, no, semi-log of x. Or log. Is it log? Okay. So what I'm trying to look at this is this. So we need to get a log of the x-axis and a log of the y. Is it log of y or is it log of x? No, it's log of x. So semi-log. We're gonna look at the power. Semi-log of the x-axis. X. See if that works. Ooh, does that look cool? Here's our pole, right? What's that number? 3 dV. What? Let's do something. Is it gonna work? It's not gonna work. I was gonna say mesh. Come on. So I want to investigate this, but if you guys want, actually don't, or if you want to, yeah. If we were looking at, okay, the imaginary axis, or okay, see this imaginary axis right here. If we just sift this out, we're actually looking at, like, see how this all curves, and here's this pole right there. If you take the actual, like, what do you call this? If you make this frequency a Bode, like a not Bode plot. Oh, it is a Bode plot. Decades, right? There's got to be a way. I forget. Mesh C. Actually, no. That's triggering my OCPD, man. I gotta find this. Okay, semi-log. Mesh C. Okay. Mesh C. Semi-log X. Is there a way? Semi-log X, semi-log Y. Logarithmic. And then this is where people just start going crazy. Except cookies. Yes, I love cookies. I don't think you have any choice. Aw, man. Well, I tried. The point is, what I'm trying to say is, you can get a Bode plot from the Laplacian domain. And here it is. Do you understand this now? Is this making sense? Now you can do all your LT spice just by punching in these S's. Does that make sense, everyone? Can everyone finish this assignment? Let me go over it one more time. And now you can do this quiz too. You can verify with, well, if you want to, you can keep going and verify with LT MATLAB. But make the delay 0 because I can't figure it out. Maybe I'll show you guys next time. But now you guys can do this via Hancocks. Recall this and just apply the same methods I was doing with the RC circuit. But this time there's no memory in your system. There's no memory. So all you're doing is just converting all these y's into s squared of y of s. Something like that, right? You guys can do this. You guys can do that for homework. This one for homework, this one for homework. And yeah, you guys can have fun about that. And oh, the residue function. Let me just give you that. Did I give you this? How to use residue function. Man, if you guys don't know how to do that example, it's because you're not reading these assignments. This is probably one of the easiest assignments, so if you can read this. So I bet everyone can finish this first half of the assignment, hopefully in a couple days. You can literally finish this in like 20 minutes. No late excuses. Any other questions? All right. Have a good day, everyone.